Hey, welcome to Ones and Zeros. My name's Ben, and today we are doing another episode of our FPGA Basic series. I believe we are doing episode 4 today, off the top of my head. Rather than looking it up, I may just guess. Where are we? Yes, we are doing episode 4. Wonderful. I do apologize. I have done 2 other videos already. This is my 3rd one for the night. The last one took 2.5 hours. There was a nice little bug at the end of that video. So if you want to see some really cool STM32 debugging, check out our new episode of our Discovering STM32 series, where we take a look at getting a driver written for the Quad Spy peripheral and flash memory. It's kind of fun. But we're not here to talk about STM32. We're here to talk about FPGAs. And we are, of course, going to be using our good old Terasic D0 board, as we've used in some of the previous videos, kind of in the road of being able to see what's going on there, but you can see that one. So set up exactly the same as we did in our clocks video. So we've got our STM32 board sitting here. All it's doing is providing a 4 Hz clock over to our Terasic board, which we might just turn on, so that we have a slower clock to use as a bit of an example. We're going to get into PLLs in the next video, where we'll actually start to make use of the 50 megahertz crystal that is sitting on the board just there. But for this video, we're going to have a look at something that is really quite useful when it comes to keeping code organized in a FPGA project, or in this case, Verilog HDL, utilizing the Altera Cyclone chip, or in this case, Verilog HDL using whatever chip. So what we're going to look at today is a thing called modules. So modules are a way of allowing you to organize your code a bit better, keep things a bit neater, break things up into sections a bit better, separate things across multiple files, and generally that's going to help when you start to develop bigger designs where you're going to have a bunch of separate pieces that need to be able to have some connections to each other, but where they're effectively separate systems or separate subsystems. Because that way, whenever you're going to work on that particular subsystem, you're not going to be having to go through a mess of code that includes everything. You can just focus on the module for that specific system. So let's do a bit of a diagram for this one. So you can think of this a little bit like, hopefully this is going to work, maybe. See if we can make it work. There we go. All right, it's just being a bit slow. My pen doesn't want to behave itself. Let's just erase that bit and draw a diagram. Go away. There we go. All right, so if we imagine we're going to have our top level module, which in the videos so far we've been calling that one QA main. So let's just draw a box to represent that module, and we'll call him QA main. We've got a bunch of inputs and a bunch of outputs going into and out of that module. Inputs and outputs, which allow this module to connect to the outside world. Now, this in itself is a single module, and you may have noticed that from some of the code we've done previously. However, we can also have other modules, and typically in a project, you're going to have your top level module, in this case QA main, and then we can have other modules inside it. So today we're going to look at creating a reset and clock control module, which is not going to have a great deal of functionality in it because the main focus is how to use modules effectively. We're going to be expanding upon that in future videos. Now, this module could have other modules in it, which we're going to look at in the next video, because the reset and clock control is going to have a PLL module in it. And then we can have other modules as well, adding other functionality. And these modules can be wired up to inputs. They can have their own inputs and outputs, which might be wired in between modules. And we could have other modules that have outputs that are going out of our main module as well. So that's kind of a bit of an explanation. And through doing this, it allows us to have a particular bit of Verilog code for each module. And we could have this one, which we're going to look at today, which will be in a separate file, for example. So that way we don't have to stuff all of our code into a single file and, like I said, end up with what would potentially be a bit of a mess. So it's a really handy thing to know and know how to use. We've got our project set up similar to how we've done it in the last video on clocks. So just got our top level file QA-main.v and our top level entity, which is a module. And it's a module called QA-main. In this case, because it's a top level entity, we need the module name to match the file name, which is why both the file and the module are both called QA-main. Had too much coffee this morning. It's nearly 1 a.m. So yeah. So in this case, we have the module. We're defining it as a module, giving it a name. Then we have our parentheses. Inside the parentheses, we're defining a bunch of inputs and outputs. And then after the parentheses, we have the semicolon, and then we have our code for the module in here. And the end of the module is defined by the end module keyword. So that's kind of the pieces that go through to define a module. And let's just create one that's a little bit simpler than our QA main. And we're going to create this one in the same file, just so you can sort of see that we can do that as well. And we're going to create a module for what we're actually doing here. So we are, in this case, setting all of the bits that are controlling our 7-segment displays to 1s, because with the 7-segment displays on this board, if we send a 0 to a segment, it turns on. If we send a 1 to it, it turns off. So we want to have all of those segments turned off so that they're not distracting us from what we're trying to do with the LEDs. Just looks a bit neater when we're doing stuff with it. So let's call this module 7-segment. And we're going to get onto another module that does a little bit more in a moment, but we're just going to create this one to start us off. So as I said, we're going to have module, have the name of the module. In this case, I'm going to call it 7-seg module. And I'll explain why in a moment. And then we have the parentheses where we're going to put in our inputs and outputs, and then we have our functionality in between that and end module. It's important as well in a file to always have a blank line after end module, because if we don't, as we see, end module turns black, which means it doesn't quite understand properly. If we put a blank line or two after it, then it knows that it's the end module keyword. So if you run into that sort of an issue, that might be why that's occurring. Now, in this case, we're going to want some groups of outputs. So we're going to need to output values for these guys. We're going to do it a little bit simpler though. We're just going to have one output that we define in here. Now, each of those 7-segment displays requires a 7-bit signal or number that is being supplied to it in order to be sent to those. So in this case, we're going to go 6:6 0 to let it know that we need bit 6 down to bit 0, which gives us the 7 bits that we're looking for. And let's just call this 7 seg out. Actually, we can't put a number in the start of it. Let's just put segment out for that name for that one. If we were putting multiple inputs or outputs, we'd put a comma after it, and then we could put another input or output or whatever after that. The last one doesn't have a comma after it, as you can sort of see from this here. So these guys have commas at the end of them. The last one doesn't. It's just kind of the way that gets structured. And then inside this module, the actual functionality of it is just going to assign segment out to 7 hex 7F, which is our 7 bits. We could, as I've explained in previous videos, we could also do a binary number, which is telling it how many bits, whether we're doing hex or binary or whatever, and then the particular value. So in this case, 7 ones to represent the 7 binary bits, or we could go with hex as we had, where we just do 7F to represent 7 binary ones, like so. So that's a simple module, and how we go about actually using that is we're going to create a wire that we can connect up to these 6 7-segment displays. And let's also call this seg out, because that kind of matches with what we're doing. And we need to let it know that that's going to be the right amount of bits as well. Make sure I'm getting this correct. Definitely need more coffee. Let's go with that at the moment. I may be wrong. Having trouble remembering whether this goes before or after the name, which I should be able to remember, but sleep is a thing that's going to happen soon. All right, so let's go with that one. I feel like I haven't got that right. Let's just double check that. Where are we? No, I think that's correct. I think I had it right. So let's stick with that. So then we're going to create our module. Apologies for that. So first thing we need to do is give it the name of our module declaration, which in this case is QA7seg module. We're also going to need to pop the definition for this one up above here, because we need to define it before we use it. And we're going to call it 7seg. Now we need to, so we're firstly giving it the name of the module definition, and then we need to give this instance of the module a name as well, which is what this one is. That's why we put module here in the name of the module definition, so that, because I know I'm only going to use one copy of this module, that way I can just use QA7seg for the name of the instance of that module. And then we're just going to supply it with the particular wire there, so that it connects seg out to our output that we've got there, that we've defined. And we'll sort of see how that works when we do the next module as well, a little bit more. So so that you can see how it works in a situation where we have multiple inputs and outputs. So in this instance, we can now just go seg out for all of these guys, and that way they're all going to receive the same value from our 7-segment module. So that's kind of how that works. So this is our module declaration, where we declare the module, what inputs and outputs it has, and what functionality it has in it. And then in here, this is where we define an actual instance of the module, provide it with the definition name, an instance name, put in the inputs and outputs, and then we're good to go from there. Now, we can also create modules that are in other files. So let's get us another file, a Verilog HDL file, and we're going to create a very, very simple reset and clock control module for this one. 23rd today. This code that I was using for testing was written yesterday at this point. So, all right, we tell it we want to create a module. In this case, we're going to call it QA RCC module. Put our parentheses in so that we can put our inputs and outputs in there, and then we want to put end module at the end so it knows that that's the end of that one. Now with this one, we want to bring in things like our reset signal, our clocks, as well as a signal to be able to select whether we're using an automatic or manual clock, similar to what we're doing in the previous video. So we're going to define an input to bring in our low active reset signal. We want a input for our manual clock, so the one that will be connecting to one of the push buttons so that we can clock things manually. We want one that's connected to our automatic clock, which is the clock that we have coming from our STM32. We also want a signal coming in to be able to select between our automatic or manual clock. Now we're going to have a couple of outputs, which we're going to call system reset and system clock. So these are the reset signals and clock signals which would get distributed to all of the other parts of the system effectively. So that's given us the inputs and outputs that we want. And then we're going to assign to our system reset signal. And because our reset signal is typically low active, we might just invert it to turn it into a high active signal. So we're just going to go the invert of nReset in. And then we're also going to assign to our system clock, and to allow us to select between our manual or automatic clock, we're going to go clock select in, clock manual in, and clock auto in, which basically creates a bit of a multiplexer, so that if clock select in is high, then it's going to allow clock manual in to be connected to sysclock. If it's low, it's going to allow clock auto in to be connected to sysclock. So easiest way to create a simple multiplexer in that situation. And that's basically that module. So that just allows us to show how that's actually going to work. Now we're going to save that file and we're going to call it QARCC.v, like so. That one should automatically get added to the project for us as well, so we don't have to worry about that. And then we're going to go and pop this module into here. So first things, we'll create a few wires. So clock manual in will be the inverse of key 0 or push button 0. And because that's an active low signal, we're just inverting that so that it becomes an active high signal. We're going to go clock auto in, which will be coming from our microcontroller, which comes from GPIO 0 pin 0, and our clock select, which is coming from switch 0. Now we also want a wire for our system clock and another one for our system reset so that we can hook those up to the module as well. And then we can just go QA-RCC module, which is the name of the module declaration. We're going to call that QA-RCC, and then we need to hand it the respective inputs and outputs. So first one of those will be our reset in, which will be our reset end signal. Then we need our manual clock input. So clock manual in, clock auto in, clock select. Then we've got our system reset and system clock signals there. So we can see if we jump over to here that matches up. So reset, manual, auto, select, and then our system reset and system clock. So you want to make sure that the order that you're putting in the signals here matches the order that they're declared here in order for the signals to be connected up to the right spots. If you need to be able to view files side by side to make that a bit easier, especially if you're using multiple screens, it can make it a bit easier. If we go over to this one, we can actually right click on the tab there, go Detach Window, and that allows us to pull that out as a separate window and makes it a bit easier for us to be able to refer to different bits of code as well, which can be a bit of a bonus. And then if we want that back where it was, we can just go to Attach Window and jumps back on there where it was. So that can make life much easier. And then what we're going to do is we're going to assign to LED R0 our system clock. We'll assign to LED R1 our clock select so that we can see which clock we've got selected. And just for the sake of it, let's also assign our system reset to LED number 2. Now we could do it that way, or as you would have seen in the previous video, we can do the same thing by going to assign LED R, and because we've got 10 of those, we can do a squiggly bracket, and the first 7 of those LEDs we're not going to be displaying anything on. So we can just make all of those 0, and then we could go system reset, clock select, and system clock like so, which will do exactly the same thing as what we've done here. If we didn't want to have to put in this bit, then we can also just go LEDR2:0 so that it knows that we just want to assign to those 3 bits. And then we could use the other 7 LEDs to do other stuff just by assigning to those either in this same line or on other lines if we wanted to. So that's kind of how that works. Let's check to see that this compiles, or see if we end up with some bugs. Hopefully not. Kind of had enough of bugs filming the last video. Was a bit of fun though. Got 2 hours and 10 minutes into the last video. Wasn't sure I was going to solve the bug. Decided to give myself another 20 minutes and solved it with 3.5 minutes to spare. So it turned out to be a win, which is cool. So it's nice to do something nice and easy like dealing with modules in Verilog compared to the last one. So just getting our fitter stage done now. Find the modules can be really useful in a bunch of different cases where, say, if you're developing a microcontroller in the FPGA, you can have the CPU as a module and the memory controller as a module and, say, a timer peripheral as a module, and then just have all of those in separate files, which keeps things simple. Or even inside a CPU where you can have the arithmetic logic unit as a separate module and the instruction decode as a separate module and things like that as well. Generally makes things much easier. Well, we have successfully compiled, which is always a bonus. One thing I'm going to do is make sure that we have the correct software on the STM32 so that it is actually acting as our clock source, which is this bit of code here. So we'll pop that onto the STM32 to supply that clock signal prior to putting our compiled Verilog code onto our FPGA. Let's pop that over onto our other screen. That's just getting it copied across now. Wonderful. And let's go through and program our device. So again, just going into add file into our output files directory and selecting the SOF file. Now you can also set this up so that it doesn't require you to select the file each time, and we'll have a look at that while we're in here as well, because I haven't shown that in any of the previous videos. So just getting that code put across onto our device and all programmed. So we can see with the switch, we've currently got our manual clock selected. So the clock will pulse high anytime we hit the button. If we switch that, then we can see that we're getting our 4 Hz clock from our STM32 device. And if we hit reset, we can see that the light lights up to let us know that our reset signal is active. Now we can do other stuff which we'll look at in the next video, such as shutting off our clock signal anytime that we're in a reset state, things like that. But this just kind of shows, again, how to use modules. So let's jump back over to this one. And as I mentioned, we can set our programmer up so that we don't have to select our file each time as well. So when we go to close the programmer, it's going to ask if we want to save it. And let's just save this as SOF chain, because there is the POF file, which we'll have a look at in a future video as well. So using the SOF file means that we'll program the FPGA, but if we power it off, it's going to lose the programming. We can use the POF file to allow us to have that stored in memory so that the FPGA can load that automatically every time it starts up, so we don't have to reprogram it each time. But for the moment, we're just going to use the SOF. We'll save the other one for a future video. Now, we can see in our project navigator when we have files selected that our SOF chain file that we've just saved shows up there. So if we want to reprogram it using the same settings and the same file again, just double check that, double click that, and it will open that up ready to go, and we can just hit start to program it. Now, even if we recompile it and it updates the SOF file, we can just use that same chain and it will still work fine. So that's kind of how that works. One of the other handy things that I'm going to throw into this video as well, which is how I learnt quite a bit of Verilog, is in here, if we right click, we can actually go to insert template. We've got a bunch of different options here. We're going to go to Verilog, and we can see we've got a few different things here, such as logic, constructs, full designs, etc. If we go into, say, one of these, say a register, let's make this bigger so that we can actually see what's going on. There's a bunch of different types of registers that it's got here. If we go with a basic positive edge register, we can see sort of an example of the code that we're going to need to make that particular that item, that basic positive edge register. Now we need to replace the stuff in the greater than less than symbols with our own details, but it does give you a bunch of different templates for different things. So if you're not sure how to create a particular thing, this can be a really helpful way to do it. So say if we wanted to create a shift register, we've got some various different options in here that we can look at. It's a good way to sort of get a bit of an idea of how certain things are done, but we're going to be covering all of this stuff in the videos anyway. It's just if you want to sort of dive in and have a bit of a look, checking through the templates can be a really useful way of finding out how certain things are done. So that is modules. That's how they're used to be able to help break up the code a little bit, make things a little bit easier. Generally, any functionality that I have in a project is going to be in sub-modules, and the main top level module is only going to be used as a container to hold those additional modules and to wire them up to one another and to the overall inputs and outputs of the FPGA. Find it's a much neater way of doing things, and generally, especially because FPGAs, if you're new to them, can be quite confusing sometimes. So it's a good way of breaking things up so that they make a bit more sense. And then we can go through things like with our reset and clock control module, we can add functionality to that without having to worry about how it's affecting the rest of our code, with the exception of inputs and outputs. So if we add or change or remove inputs or outputs here, we need to make sure that we're also making those same changes in here. Otherwise, things aren't going to be connected up properly, and you potentially end up with compiler errors. So that's modules. Hope you found that interesting. It's a really useful thing to know. Just to help out, I am going to put this code up onto our GitHub in the FPGA Basics repository under episode 4. So that'll be there so that you can, it'll be basically the QA main V file and the QA RCC V file. I won't put the entire project in there, just the Verilog files, so that you'll be able to grab hold of copies of those or refer to them on the GitHub page, things like that, to make it a little bit easier for you. So if you like this video, love it if you hit liked, subscribe if you haven't. Thank you to all of the people that have subscribed and liked and left awesome comments on the videos. It definitely helps inspire me to keep making more. Although I'm definitely not doing another one tonight, because after a bunch of hours and me nearly losing my voice, I think I'm done for the night. I'd like to say a big thank you also to both Craig and Luther, our 2 patrons at this point. If you do want to help support the channel, there is different tiers available on Patreon, each with their own sort of set of benefits and things. You do have a private Discord server set up so that you can chat with me and other patrons as well about questions or projects you're working on, whatever. Yeah. Other than that, we do also have a subreddit. You can drop questions there or in the comments under the video. I do keep an eye on both of those. We've got our GitHub, Patreon address, and also the email if you need to contact me that way. So hope you all have a wonderful day or night or evening or morning, whatever it is where you are in your part of the world. And thanks for watching.